All right, folks. I think we'll go ahead and sort of get started. Welcome to the Go Meetup. Once again, quick reminder, I think everyone's been here before, but in case you haven't, boxes above you with the green lights are mics. They are designed to be sensitive to pick up questions in the crowd. That means that if you say something during the speaker's talk, you will show up in the audio stream for the YouTube video. So please be mindful of that. If you want to speak, we do have a pay per call link. I think we have used it once in the years that I've been here. Really just come talk to me, talk to Carson. Mariah you're not supposed to talk to her, but if you do, she will direct you to us. So, but yeah, we are happy for anybody who's interested in giving a talk. We do a mix of shorter talks and longer talks. So if you're like, hey, I would like to give a talk, but I can only put together 20 minutes, that's fine. Talk to us. We'll work with you. We're working on the standard library right now. So go find a standard library package. There's still a lot of them we haven't covered. They're great topics. There's a ton of stuff in there. Jobs and hiring. I know that networking is a big part of why people come to these. Most of that is going to take place on the Forge Slack. There's a jobs place where you can look for people who will post jobs. There's also a seeking jobs place where you can post your resume. I have seen a lot of people use it to interact with other people in the Forge community and go grab lunch with people to learn about their org. And we've hires through that channel. So if you are looking for a job, that's the place to go. Also, there's fun stuff that happens there. So even if you're not looking for a job, come join us. We talk about all sorts of fun stuff.
Is there a list somewhere of what Go standard packages have been covered already?
Yes, there is. I think it's in the Forge Slack. If you go to is it Go Meetup or
Go channel?
The Go channel.
Slack Canvas, which is like a wiki.
Yeah.
The tab. Okay.
So if you go to Slack, go to the Go channel, and then go to Canvas. There's a list. We check them off as they happen. Also, you can just talk to us, and we will let you know what's available. Weave is hiring. Weave sponsors this. They pay for the food. They let us come meet here. So we are happy to talk about the jobs that are open. I think we have some senior software engineering jobs, some AI focused jobs. So please apply and come work. You'd be on my team. I think my team is hiring. I'm pretty sure we've hired a ton of people. So go check out the careers page. There's good stuff there. I'm going to go ahead and turn the time over to Carson. If you've heard a talk from Carson, he's incredible. We're in for a real treat. I'm very excited. He always gives super great talks, but he's going to be talking about the hashing library from the standard lib. So go ahead and everyone clap for Carson. Yeah.
Thank you, Brandon. Okay, this is going to be one of those talks that's almost on the nerd level of the math talks. If you're here from some of the math talks, so if you liked those and you like that kind of what the heck's going on and what is otherwise seems like a simple thing on the surface, you're gonna love this. If not, it might be a little strange for you. But I'm gonna keep it really entertaining. Stay with me on this. I'm covering the hash package, and let me just pop over to my thing over here. So quick introduction about me. I don't like to spend a lot of time in my talks talking about me because who cares? But
I do.
Thank you. All right, I appreciate that. So my name's Carson Anderson. I've been here at Weave for almost 6 years. I am officially if anyone's asking me on LinkedIn, I'm a principal engineer. If you ask me in person, I'm consider myself the dev XO. That means I don't technically even lead the team, which is weird because I'm a principal, but I'm not the manager of the team, but I am the one that kind of makes it so. I am the one that has the ideas and executes on the vision, and that's the title that speaks to me. So that's what I prefer to say that I am. It means almost nothing except for, I'm making it happen for someone else kind of taking that direction. That's me. And so we're going to talk about hash. And if you go to the standard lib and you go to the Go docs, and you click in and you can just follow the source code for the hash package, you're going to find that it's really, really, really small. If you just import hash in your Go code and follow it in, it's less than 100 lines, 96 lines as of that specific version of Go. So there is almost nothing in the hash package. So what the heck am I gonna do for like the rest of the time to fill our space, right? And I actually picked this not just because it was one on the list, but because I have a pretty strong passion for the problems that hashes solve once you understand primitive, like the technical level, what hashes can do. Suddenly it opens avenues for building things and solving problems that you otherwise would think are insolvable, or you solve them using way more difficult solutions. So I'm just spending a lot of time talking about other stuff, but stay with me. I have toys. Let's start out with this, and I'm going to explain why I have Mr. Gopherhead. When I thought of the hash package and I think of hash, I immediately think of potato hash. Hash browns, like literally potato hash, like a big plate of hash on a skillet. And then I went straight to Mr. Potato Head, and then I thought the gopher is just ready to be a Mr. Potato Head because it's already kind of potato shaped. And so, what's that?
Mr. Gopherhead?
No, well, we kind of are. Well, yes, we are. We're going to kind of hash Mr. Gopherhead. So if you also have seen it in my talks recently, I have committed to paying humans to make human art for every single talk that I do. And I do not do any AI generated anything for my talks, including the art, especially the art. So I didn't have to pay anyone this time. Spoiler alert, my wife did this. So she wanted to do this. So he drew this up and submitted, which saved me a little bit of money on paying somebody for art. But I kind of led with this. So you're going to see him a lot throughout the rest of the talks. And I'm so obsessed with this idea. And if you were here from my Go West talk last year, you might remember there was a big 3D printed tree, an AST syntax tree that I like taped this. So today, instead, I brought gophers. I brought many iterations of Mr. Potato Gopher. And they're not just, if I can pull them out and try not to drop it. They're not just like little guys that sit on your desk, but they are Mr. Potato Gopher. You can take them apart and rearrange in pieces to whatever you like.
ForCon is this week, and they're not gonna have anything that.
We don't have anything that's cool. No, so I've got one extra Mr. Potato Gopher I've got like one I want to keep obviously for myself because I put a bunch of work into it. I can put another one. I've got 4 to give away. Like, what am I thinking? Why am I being selfish? I've got 4 of them to give away, including this really horrendous early draft that like the parts don't fit right. So I don't even know what it looks like. Like
That's like the potato battery.
yeah. So I have no idea what the criteria is for giving these things away. So we'll figure that out. So yeah, we already pulled apart. I had to learn Blender for this, y'all. Like I don't know Blender. I did many iterations of trying to come up with this. I'm actually pretty happy with the final result. We'll give those away to, I don't know, whoever can answer a quick question about hashes at the end. I don't know. We'll figure it out. There's also the 3D models on the source code for this slide. So I'll give that link again at the end. It was there at the beginning. So if you want to go do this print yourself, you can totally go. Okay, so Mr. Gopherhead says, let's talk about hashes, right? The hash package is really small, so what are we going to talk about? We're going to talk about this whole list of things. I will iterate it. So we're going to say, what is a hash? Like, we're going to talk about what the heck hash is anyway before we get into the implementations. We're going to talk about the use cases, which is why I wanted to give this talk, is the use cases of hashing, not necessarily how clever Go is at doing hashes, because it's, spoiler alert, Go isn't implementing hashes any different than any other language because they're standards, right? So there's not a lot of like leeway to be clever in Go. So when we're talking about hashes, it's more interesting for me to talk about use cases. Then we'll get into the actual core hash.hash interface. Then we're going to make our own hash function. This is where I think a lot of this comes together and is the most fun. So we've made our own Mr. Gopherhead. We're going to, as a group, Mad Lib style, make a hashing function and kind of write our own hash function from 0. It's not a good one, but it is technically a hashing. Then we'll talk about the rest of the hashing package, and we'll go over what standard lib gives you with regard to hashes. So tons and tons of cool stuff. Stay with me. I'm going to start with the real fundamentals, and I have a mix of different format styles of presentations I've done before. So what is a hash, right? And all hashes are kind of a version of this. And what you've got here in between these square brackets is you've got 2 bytes, right? You've got 16 bits of information. And below that, I've got 6 more bytes. And all hashes are some version of this. They'll say that this bracket bytes are our internal hash state. We're going to start at 0. We'll get later and we'll talk about like you don't usually start at 0. Usually this is not just all zeros. But every single hash is essentially a version of this. We'll take our internal state and we want to just feed it some amount of incoming bytes. Right? Those bytes might be think from text converted to bytes, like strings or whatever converted to bytes. They might be image data. It could be literally anything because it's all represented as bytes. So it does not have to be strings. We'll be using strings a lot in here. Everything in here can be fed with raw network traffic, with file contents, with whatever it is that you have that's just a slice of bytes. But every single hash algorithm just says, okay, I have, in this case, we have two. We have an internal state that's 2 wide. So we're going to eat up 2 bytes of data at a time. We're going to take the bytes that we have, pull them up into our state, use those bytes to mathematically stir the state in a specific way. It's going to seem random, but we're just doing a lot of operations, and we'll get into exactly what those are in a second. But we're going to just kind of feed those bytes in and stir our state in to come up with a new state. Then we take the next 2 bytes of input, do the same math on that set, and stir everything up again. And then we take the next set. Again, we're doing 2-byte chunks because our internal little mini hash algorithm here is 2 bytes wide for state. We're going to stir that up, and we'll get a number out at the end. The important part about every hash algorithm is, as long as you have those same bytes in the same order, the math's always going to do the same thing, right? If you say blue, I'm going to take 3 steps left, and then if it's right, and if it's red, I'm going to take the inverse of that. As long as you go blue then red, you're going to always stop at the same place every time. And that's all hashing is just taking input data and very mathematically kind of stirring. There's a lot of tricks that they use to get really good distributions and have this be even a small change in the input cause a big cascading change in the results. I'll kind of cover all that more. But at the end of the day, right, we just fed 6 bytes into our little MIDI information hash algorithm. And now we can take those bytes and have really 2 ways we can choose to represent them. Obviously, we could try to print them, but if you try to convert these bytes into ASCII characters, they're probably not going to be printable, right? There's only about 255 ASCII characters that are printable. So what we usually do is we take those bytes and say, okay, each of those bytes can be represented by 2 characters to be hex, right? So we might say that the result of hashing those 6 bytes from before is a hash of E1V3, which is what this converts into. Another way we could do this is we could take those 16 bits, smash them together, call it a 16-bit wide integer, and say, well, okay, another way to, in a nice human representable way, is just convert those bytes into a big number. Okay? And that's pretty much what all hashing algorithms do. They usually don't do it with just small sizes like this, but you get the idea. So you take these input bytes, you run it through our whatever the algorithm is. I'm not trying to represent a real algorithm here. And at the end, you say, okay, if we hash this every single time, we take those same bytes, we'll always get out E1B3, or alternatively, you could call it 5779. And that's the basics. You'll get more of this as we go. I'll run the code here, and I'm specifically not showing you the standard lib yet. We're thinking about ideas of hashing before we get into implementations details, right? So just how can hashes work? So there are 2 functions I won't show you yet that are get hash, and it's going to return the hex, and we got get hash int that's going to return the integer. Both of them are hashing ABC, right? So they're both getting the same bytes at the end, but we're just choosing one of 2 ways to represent that. Now, I'm not doing a 2-bit wide hash. I'm using one of the built-in standard lib ones, so you can see it's a lot more than 2 bits of data. But I got 2 results here. I did that. I took ABC and I said, well, one way I can hash that into a certain set of bytes, and I can represent those bytes with this big, long series of hex code. Or I can represent that same bytes with this big number. And the size of the output and the potential size of those numbers will change depending on the algorithms you use and exactly how they choose to implement things. So there's usually not and you'll see this in the standard lib, there's not a guaranteed, like you'll always have so many, for every single hash implementation will always have so many characters wide. It's a little bit more broad than that. But that's it. So if I hit run, again, as long as I'm hashing ABC, no matter how many times I hit run, I'm always going to get the same hash result. And then of course, when I represent that the 2 different ways, it's always going to be the same 2 representations. And that's the fundamentals of what a hash is, right? It is feeding in some amount of data, and it can be anywhere from 1 byte to 1 billion bytes. It doesn't matter. The math will always math. It might take longer to do more, but you'll always get a representation of that data. We'll talk a little bit more about collisions and some other things that come with this kind of way to represent data as we go further along, and especially when we start implementing our own hasher. So, okay, neat. But why would I want to do this? I have the data. Why do I want to turn it into some string of characters or a number? What does that do for me? There are a few, and I'm just throwing out the first things that came to my head and the things that I've used hashes for, right? So I think it's a great way to take, for example, a large file that's being sent. You can run that through your hashing algorithm, all those bytes, and then you get out this string. It's a relatively short string. And if you hash it and then you say, okay, it was this string, then you send it to somebody over untrusted networks, blah, 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 and they hash it and they look at it and it's a different value, then they know something has changed it in transit. In reality, when you're doing that kind of like transit checking, you usually use like signing systems where you have more credentials and you can do better attribution. But at the network level, this happens a lot underneath the hood, right? Your network interfaces are sending bytes to each other and then sending hashes so that they can verify that the stuff that went over the network wasn't broken or corrupted in transit. So it's not necessarily a thing that we do all the time to fingerprint things, but it can be a nice, handy way to just very quickly get a bunch of content, stamp this out, and say, yes, it's this. You can imagine this again. You had files. You had 100,000 files of varying widths. Some of those might be in megabytes, gigabytes, large files. Database full of like the files you're trying to get and where they are in like a bucket or something. Obviously, you don't want to look for the entire contents. You don't want to have to search for the whole content of your file just to find the match. So you could have somebody send you the file, you get the hash, and then you just go find the equivalent record in your database. This is a really common use case. This is kind of both these in a lot of ways are, put a note here, Git, right? If we go back and we hit run on this, we look at this hash, and you kind of squint and you think about anytime you've ever used Git, you get log and you look at the top, and what do you see? Commit SHA, blah, 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 right? And it's these big long things every time. And that's because this is how Git operates on everything. I have a whole Git workshop that I can link to that kind of goes into the details of this. But Git takes commits, it takes your contents of your files, it takes merge information. Basically everything that you do takes the text of that, hashes it, and then operates entirely on those hashes. And it's kind of the fundamental way that Git does things is, let me hash all the files that you have and then store references to hashes instead of the entire content of those.
One note about that, if you ever stage a file, even if you haven't committed it, it has a trace of that. It has a log that it'll keep. So if you ever accidentally like lose your changes, say your LLM unstages all your stuff, as long as it was staged at one point, you can check through. It will all be by hashes, but you can review those hashes and find the file contents you previously staged, even if you haven't committed them.
Oh, that's useful. Yeah, it's an and once it's in Git, it's forever. Right? Even if you think you deleted it and you remove the branches, like there's a lot of Git stuff that, and I think that's good to know. Like if you literally ever like made the commit, even if you undid it at some point, like until some cleanup happens behind the scenes, you can find it again. Yeah, Git does this a lot. In case you're wondering, like how useful is this? Like the entire version control, like the de facto version control we all use at this point, built on hashing. I'm going to do another run. So here's that sample. And this is here to illustrate a few things. Notice ABC is being hashed twice. That's just to prove that the first two results are the same, right? That's how hashing should work. If your hash function can't return the same results with the same input, then it's fundamentally broken. And the other one, those second two lines are to illustrate another thing I want to talk about, which is this idea that hashes, a good hash algorithm should almost seem random, even a tiny change, right? The second line is just going from a lowercase a to a capital A. But the hash isn't just a little bit different. It's radically different with a tiny, tiny tweak to the input. Yes.
It's radically different and it's a one-way only. You can't easily reverse engineer that.
That is correct. That's another, it's really, and I should have brought that up when I was talking about hashing. It's a really critical aspect of hashing is that mathematics. It's not encoding, right? It's not two directional. It is, once you do that math, there is no way to take this and know where this goes back out. You could hash every combination of things in the world until you, and then keep seeing if they match that. And eventually try to brute force your way, but you can't take this and reverse engineer what you gave into the system to get this value.
That's why I want to use it.
It's not quite accurate for some uses of hash. It's very important to note that you can absolutely, in many hashing algorithms that are weaker for different purposes, you can absolutely come up with a thing that will hash to that. So like using this as like a password or something.
Yes.
I now have your password because I have something else that hashes to your password. So keep that in mind. It's not reversible, but that's not everything that it might be.
It's not, well, it's not reversible, but it's different levels of security, and Go actually groups its hashing into crypt safe hashes and non-crypt safe hashes, right? And like,
Numbers, that is very important.
very important, yeah, so that's a good point. And you shouldn't use it for password because there's an entire bcrypt standard lib package for passwords. Just use bcrypt. You don't need to write your own ID.
Do we want to talk about hash length and hash collisions, or are you?
Oh, I'm getting there.
Later?
Oh, yeah.
No.
We will. I can talk about it anytime, but I do have some sections where we'll definitely get to the idea of.
Hey, did they win Gophers for getting good comments?
Yeah, this is, you might win one of, you weren't here for the,
I know we were late.
Sorry, I can't like,
my Mr. Gopher heads.
Hey,
can I?
They are actual
Files for that.
fixable.
They're on the slides. The files are on the slides.
The files are on the slide. We're early in the repo. So you get to print your own, but we're also giving away those that feel like they have earned it. I don't know. We'll do a vote at the end. Okay, so that's hashing as fingerprint, pretty useful. Hashing maybe for passwords, if you use bcrypt, that's a good idea. Bcrypt does all these other ideas to take hashes and make them more secure and harder to guess. And definitely we'll get into the different algorithms have different levels of security. Here's one that I use a lot as somebody has to build platforms. I live in the world of Kubernetes and clouds, and clouds and Kubernetes love, and I'm between users who want to write verbose long names that describe things or need to because they need uniqueness, and Kubernetes and clouds that say, whoa, like your Google service account email can't be more than like 32 characters or something very small that we outran really, really quick. So we'll talk about this. Collisions here is really where that comes into play. But again, without showing you implementations of how to do this, I've got this function. We've got a hash function that will get us an integer, right? So we give it a string here and we'll always get the integer back. And I'm going to call that integer, I'm going to just make a string that's ID and print that. So really, really simple. And what we get is, if I put this down, right, this really long user provide and said, yeah, but I'm going to shove it somewhere where I can't use a string that long. So I'm going to condense it down into this seemingly random number. And then Kubernetes will happily take this as a label value. Like you could, I think even this could be a better example if we put, I can actually do it here. If I put like, weird characters and stuff that maybe.
A space.
Yeah, Kubernetes hate that. You couldn't take Kubernetes and say, or cloud and say, this is the instance name. Like that won't work. It's very obvious that the user doesn't give you clean data and you can't always control user data. I think I put one too many. Yeah.
Or if you have user input somehow getting in there and someone tries to name their service after little Bobby Tables.
Yeah, they're a little, yeah, exactly. Someone wants to name their service at little Bobby Tables. This is a pattern I use a lot. You make kind of a pseudo ID. So you give me the thing, I'm going to run it through the hash algorithm, and I'm going to either convert that into the hex codes, which work sometimes, except those hex codes for most of good algorithms are really, really long. But also, several of the algorithms can give you an int. In this case, it's int 16. So a relatively short, knowable number, where as long as you always do that same input, you'll get the same output. And Kubernetes or whatever will happily take this. Now, there are downsides to this, and this is where we talk about collisions, right? If I'm taking a potentially infinite amount of data and saying I can convert that into math to represent it in a finite space, you get into what the hash people call the pigeonhole problem, where it's essentially like, if I've only got so many unique combinations of 16 bytes, right? If we go back to our 2 bytes from before, if there's only so many unique combinations of 2 bytes, it happens to be the number, the highest like max int 16 value plus 1.
You've got 2 to the 16th combinations.
Yeah, exactly. You've got 2 to the 16 combinations, and that's it. That means eventually, given enough things feeding into the system, 2 of the things you're going to give me can collide or more, right? Any infinite number of things can collide because I have to represent it in a smaller space. I've only got so many combinations of that.
If you're supremely unlucky, things number 1 and 2 will collide.
Yes. And this gets to where good hash algorithms have a lot of what they call dispersion, where those tiny changes cause radical, like even again, just a single bit difference will cause radical different results. And you just play the numbers, to be honest. Depending on the use case, you either play the numbers or you trust but verify. So in cases like this, where we build a platform and the users are giving me a weave, they're deploying things, they're naming things. I need to make Kubernetes stuff with a shorter name. We generate that, and then see how we're going to hash this. Before we let you go through, let's just check in a quick database to make sure that it's not duplicated, right? So we'll do this a lot in our platform, but then we'll kind of check the results against some known list because we 100% can't allow collisions. There are also times where with certain hashing algorithms and certain logic, like a lot of the bigger hashes, the odds of collision are so, I mean, we all do this with UUIDs every day we do UUIDs, right? UUIDs technically are not guaranteed unique and can collide, but the odds are so far that you just assume it's 0. So again, the hash, depending on the length of the hash algorithm you choose, and we'll get into all the different lengths and the standard implementations, give you a different likelihood that you will have collisions. So it's not 100% guaranteed, but it's one of those things where you just kind of play the odds and it ends up working out enough that risk it. If you can, for this like pseudo ID thing, it is a place where in certain critical scenarios, I will hash it, but then we will have some sort of like 100% guaranteed where not in Kubernetes, but in some database where I can have the two side by side, have that list of what hashes exist to make sure if you have a collision, we'll just reject it and say, sorry, that name, you can't deploy that name something else. So we'll get a bit more in that. There's one of our use cases. And this is my favorite use case, maybe why I did the whole talk, hash bucketing. Hash bucketing, y'all, seems like magic. It is one of my favorite things since I discovered it. And what a hash bucket is, and I'm not going to go deep into the Go map type because there could be a whole talk and there are multiple talks and everything about how Go maps work internally. But they technically use hash bucketing. But my use case is this use case right here of gradual percent rollout of a feature. If you're building a system like I did, where you need to roll out a feature to users and you might have hundreds of thousands of users, right? And someone says, I need to roll this out to 10% of the users. And if you're a naive person, like the person before me at Weave, you would say, cool, I'll get 10,000 IDs, take 10% of them and go set the thing on for 10,000 of those people explicitly. And then that falls over after startup phase pretty dang quickly. It works great when there's 10 users or 100 users, but once you get up past that, it's a not scalable system, right? So what do I do if I have hundreds of thousands or millions or whatever of users and I want to reliably roll a feature out to a percentage of them? And this is kind of a full implementation of this in principle, right? I have a function here called getBucket, where you give it a string. It's going to get a hash integer, and I'll show you how to do this, but there's this function to just give you an int back. We're going to modulo that int into, right? Remember, it's pretty evenly distributed. Good hash algorithm, pretty evenly distributed. So I'm going to modulo that into 0 through 99. So no matter what integer I get, when I mod 100, I'm going to get 0 through 99. And I'll always get that, right? They'll always give me the same string. I'll get the same hash integer. I'll get the same modulo number. So if I want to do something like, say, if a given user could have a feature, I'll say, okay, well, I'm going to give you the user ID, and I'm going to give you a percentage of rollout level. Right? So I'm going to say, we're rolled out 50%. Here's the user ID. Should they have a feature? Yes, no. What you do, you get the bucket. You get that 0 through 99, and you say, okay, well, if that bucket is the what number I get for that user, and I'll see the examples in a second, is less than or equal to that. Yeah, they have the feature. They're part of the 50%. And I don't need a database. I don't need to know all the user IDs in advance. I need one number, one calculation, and I can support as big a scale of end users as you want. So here's an example where we're printing, we're going to do just A, B, C, D, and seeing if those user IDs have a feature, and we'll say that feature is out at 50%. So A hashes to a number that when you mod it by 100 comes to 26. B goes to 63, C is 0, D is 73. And since the feature is rolled out to 50% of users, we can say, okay, well, if you are in the percentage of users that is below, less than or equal to 250, then you have it. So in this case, A happens to be in the 50%, B is not, C is in the 50%, and D is in the 50%. And that's it. Some things worth noting about this is it's really, really useful because you don't have to use those user IDs in advance. You can just send me whatever user IDs you have. As long as you give me the same user ID every time, I will give you the same yes, no in the feature every time. Usually what you'll do is you don't actually just check the user ID in this function. You would say, give me the user ID, give me the feature name. And because those two are always the same, I don't always have the same user always getting the same feature, right? Because now I'm not just hashing the user ID. I'm saying I'm hashing user feat1. That's going to always return to a specific value every time. And then when feat2 comes around, that's going to be a totally different value for that user. Yes.
Tiny bit of pedantry. Shouldn't that be less than P, not be less than or equal to P?
It probably should because it's 0 through, well, it's 0 through 99.
Yeah,
So
but if you're giving a percentage as a number between 1 and 100.
yes, then you probably, yeah. So it probably should be less. So that's, you get the idea. This is, and this is like what, yeah, go ahead.
I was just saying, like, more pedantry, but if you do like statistical perfection, you have to be careful about stuff like modulo and stuff like this.
Oh.
Because
Yes.
the distribution of bytes is not gonna distribute perfectly across 100 buckets just because of math. So,
No, that's, well, and I, you know what? You know how ahead of me you are, and I love pedantry. You were all at a talk about hashing.
It's code. How dare you?
Here's that distribution, right? Like, it's not perfect. So I actually did that distribution. I thought this was coming, like.
Lead into my next slide.
Yeah, thanks for.
It's a plant.
It's good enough, right? It's not perfect, but it's good enough compared
It's
to.
way better than trying to hit the database to change a field on 10,000 system.
Well, yeah, especially once you're into the like 10, 100,000 users, it's gonna be good enough.
Exactly. It's, you just need the same user to get it. No one's over there measuring that it's exact, like literally no one cares it's exactly 50% of the users. They just know. No one's gonna know what 50% of the users even is at any given point. So yeah, but that's a good point. Not statistically accurate, good distributions. And if you go plug in different hash algorithms into this function behind the scenes, and we'll talk about that, you'll get different levels of distribution. So we can look at the code. You go look at the code I used for this one. We'll talk about the algorithm, but some of them have better distributions of these. So I will show again, if we were to change all of these to feat 1, which is what we usually do. And internally in our system, we have a feature flagging system that uses this behind the scenes. And we always feed the name of the feature in. We want some user to be the poor schmuck that is always 0.001.
Beta tester.
It's the earliest feature every time. So we feed seed, like essentially you just need to feed the same value for everybody, but you can absolutely seed different data. If I hit run again, I think they actually ended up the same. That's kind of funny. I didn't put it in the right place. Sorry. Feat 1. I have to put it in 2 places because. There we go. So now it's true, true, false, false. Like we got a totally different distribution just by seeding of the feature name. And this works exceedingly well. I'll say a little bit about Go's underlying map type. Go does this. You can go look at whole talks on the Go's map type, but it takes the bytes of what you're trying to put in your map, hashes that, and then makes a certain number of buckets and says, okay, just like we did, right? Say you had a map in Go and it had 100 buckets here, and it's going to say, okay, well, these 2 values belong in bucket 0. These values belong in bucket 1 or 12. And then inside those buckets, it's just arrays of data. So Go is doing this thing with the maps internally, and I'm probably getting it wrong because I'm not getting very specific on Go, but in a lot of languages, they weren't called maps, they were called hash dicts or hash tables. Yeah, what do we all call them? Something with hashes in there. Like they were more like direct in your face, like, yeah, we're using hashes for this. Hash maps, yeah. So Go is still a hash map, it just doesn't call it, it just calls it a map.
I mean, that's the same. Python dictionaries are just hash maps.
Yeah, it's all hash maps because that's what works. So I love hash bucketing. It is a great way to make a feature roll out. And again, here's the whole implementation sort. Like if you need to do this in your service and you just want to like slowly roll it out and you can change a number through an API call, like you can do a rollout without any backing service. You can just, oh yeah, we'll make this call and change that number to 10, and then we reliably roll that feature out to a subset of users or whatever IDs you can feed in here. It's also a really good way to do like pinning between, and you can split it into like, now you have users will always reliably go to instance 0. If you were to say I have 3 instances of something, I return this down instead of 100 to 3. Right now I can say I got 3 instances and I want to make sure this user is always going to 0, that user is always going to 1, that user is always going to 2. It's a pretty cheap, there's obviously management issues with that, but it's a really easy way to pin users to instances by hashing their IDs and then routing them by the result. So my favorite thing, the whole reason I did this talk, I did the talk about distribution not being perfect. So let's finally show some of the hash package now that we've gotten into it. So the entire Go hash package is 4 interfaces, right? It's just interfaces. There are no implementations in the hash package. So when I sat down to the talk, I'm like, okay, yeah, there's just 4 interfaces. A version of this is I could just show you these and we can be done. but we're gonna actually dig deeper. So this is the main one. This is the standard interface that all of the standard library hash implementations share. All of them will implement the hash.hash interface. And that really means they implement 5 methods, right? We're embedding io.writer, which has just behind the scenes, it's got a write function on it. So you can write some number of bytes and get the results written and an error. So it's just, I know there's an embedded here, but it's just 5 methods. That means all the hashing, like no matter what you plug in on the back end to do the hashing, where I was talking about like that distribution earlier, we're running this. I said, if you use different hash implementation in Go, that's just swapping one created struct for a different created struct because they all satisfy the same interface, which is this hashing interface. I won't go into details here because we're going to implement one. So it'll make a lot more sense when we actually go into there. This is the function usage I wasn't showing you before, or part of it. This is how you use all of those hash implementations. Typically, you create a new one. The way you make a new one is different between implementations. We'll see that when we get to our comparison slide at the end. Most of them use a .new, but some are a little more complicated than that. All of them, again, here's the IO writer. So you can write some number of bytes critically, and I'm going to if I go back to the slide one more. It never returns an error. So if you have a bad linter or some bad code helper, it might think you need to check errors every single time you do this h.write. You do not. They will never return an error. That's a promise. It's IO writer interface. It's just there for interop between like reading things from a file or reading bytes from a network connection. So it's implementing a thing that can return an error, but you can just ignore. It's one of the few places in Go where like, forget the error. This is the canonical safe way to do it. Ignore the errors. Then once you've written some data, I'm just writing one chunk, but you can write as much as you want. You get the sum. This nil is also pretty much canonical. It seems weird that there's just this bare nil in all of the like sample minimal use cases when you go to use any of the hash implementations. They all take this. If we go back, let me go back and forth on these slides. If we go back to sum, it takes this slice byte. And if you read the instructions, it says it's going to append the current hash into B and then return the result. And you think, okay, well, what is the use case for this? Like, I can just like literally say, okay, do the hash. Here's a slice of bytes, like put the hash at the end of this for me, please. Like it seems a little bit weird. And the main use case for this is to reduce garbage collection. If you're making hundreds of thousands of hashes and you have it make a new slice every time, that means it has to clean up a new slice every time. Whereas if you can allocate, right, if we know for a fact that SHA-256 is going to generate 256 bits of data, you can make a buffer, set that buffer, nil it out, and then do the next one and nil it out. Yes.
So it appends to the slice, it doesn't overwrite the slice?
It appends the slice. That's important. Yeah, it does not overwrite it. It just appends onto it. So the main use case for that is using a buffer so that you don't have to reallocate memory every single time. And that if you're doing a lot of hashes, that can be a significant performance improvement. If you give it nil, it's going to do the normal Go append thing, which is when it appends to nil, it's going to just make a new slice and send it to you. So you don't have to do anything here. Nil is very, very canonical. And if you're doing lots and lots of hashes, look into how to use a buffer. I don't even show examples here because all my use cases are never making enough often enough that I need that buffer.
If you pass in a slice, does it just return the address of that slice?
It can potentially make a new one. It won't actually return. So it'll do whatever the append behavior is. So we'll actually play with that a bit after the example. I think that's fun to play with. So you sum it, you give it nil, it's going to give you the resulting bytes, right, of this after it's been hashed. Then we got to do something. We got to encode that because we try to print those bytes. They're not going to be something we can see typically. So this is where we usually use something like hex and just say, okay, we're going to give you those bytes, encode it to a string, and we'll print that string. So I'll do this here. You can see this is the SHA-256 sum of I Heart Mr. Potato Go. If we can play this, and we can do this even more, and if we were to give it a slice byte here, the same as nil, it's going to have the same exact behavior because we haven't, right? This was just, it append when under the hood, like if you go click in on the .sum implementation of all these, under the hood is just doing an append on the slice that you gave it. Technically, you can do things like, you know, your own, right? Like slice here and send it, and it will append it at the end. Now this just got a little bit longer because I hex encoded that. these resulting bytes. So like, again, the use case isn't to actually to send it something with data at the beginning. The use case is to make that byte slice. And then in a loop, in a hot loop, you're like writing to that section of memory, then zeroing it out, then writing it to the next time and zeroing it out, instead of constantly reallocating slices and then having them get cleaned up. In my practical use, I've never done anything but nil here. It just looks a little bit weird the first time you do it, but it's canonical kind of use of that. So that's how any implementation, I use SHA-256 here, but once you're done with this creation part, they're all going to work the same way. They're all write. You can do as many writes as you want, right? So it's not limited to one. If I were to go in here and write it again and run, I got a totally different hash in here. And I do those writes, but as long as I always write the same bytes every single time, I'm going to get the same result back out. So I'm going to show that some more again, kind of drilling home on some more examples of SHA-256, hashing slightly different versions of the same string or radically different strings, and just showing that good distribution. I'm going to harp on this because this is what good hash algorithms do, and it's important because you're not going to see that in the one that's coming next. So I think that really helps this click for me of like, it's fun to say like math happens. That's what I've always done until this talk. But like, we just write our own hash algorithm, and yeah, you can, and it's going to be bad because we're not like, these are like well-defined iterated standards that people spend their whole life thinking about the best way to do these. But you can write your own, and there are like, go libraries on GitHub of like people with their own hash algorithms that they've written that they think are better at whatever.
Just join.
So we're gonna write Hugo, where we hash up the gopher. This was Mariah's question about hashing the gopher. Yes, we're hashing the gopher, Mr. Gopherhead. First, we're gonna do what is kind of like Mad Libs, but like the nerdiest Mad Lib you've ever done in your life. And that is, we're gonna fill out, we don't need to understand these yet. They'll all come back. So kind of understand this one, because there's those brackets at the beginning, those two brackets of 2 bytes, right? That was a 2, we'd said state size 2, that would have been that slide from the very beginning. What state size do we want our hash algorithm to be? It can be any number. Multiples of 4 are best, but we can do anything. 4?
16.
16. All right.
37.
48.
300.
48.
We'll do smaller ones. Let's do 15.
-2.
Okay, we're going to do 15. There's going to be a point where we're going to mix things with each other. No, it's not a multiple 4. It doesn't matter. We're going to mix things with each other. How many times are we going to mix things? Any number here?
73.
25 million.
How about a byte? We're going to, when we do these mixing, we're going to stir in the same byte every time, but just a byte.
FF.
Okay.
Byte to mix it.
After we do some of our operations, we're going to kind of take the ones and zeros, kind of loop them around. If you've ever done Pac-Man, imagining the ones and zeros going off the left and coming back on the other side. We're going to do that some number of positions over. What number should that be after XOR? 7. All right. How about the same thing after we do mixing? We're going to do that Pac-Man.
22.
22. We're going to see how good we are at this. And then we're going to also mix a byte with another byte in state, so many positions away, wrapping around. 88. Good enough. Okay. So that's almost all of that. Since we picked a state size of 15, we have to do a few more things. So there are 2 kinds of operations that we can do. We already talked about one. We got XORs and we got multiplication operations. And we can do those in any order and any amount. I have 1 of each. So anybody have any ideas of like XORs and multis? Got some, should we do, I don't know, 3 of these, 2 of these, mix them up?
Mix them up.
I'm just go crazy. You guys tell me when to stop.
Don't say anything.
I would just do every other, yeah.
Like the Olive Garden.
Okay, that's good enough. So these are all our operations we're going to do. Then finally, we chose a 15. So we have to pick an initial zero, it's not really 0, an initial state of 15 bytes. I've got some select 4-byte chunks of the byte representations of various strings, and we need to combine enough of those to get to 15. So what we've already got.
That's why you said multiples of 4 might be convenient.
But we can do whatever, right? So we just need some extras. So 4, 8, 12, 13, 14, 15. So You want to do 0 pi, like, so we'll pick 3 of these and then just add on some extra bytes at the end. What 3 are we gonna go with?
12.
3.
So we'll pick, sorry, 3 of these, 4. So we want pi?
Go.
Go, go. And then one more group of 4. 8, okay. That gets us to 12. And then we just throw in from another one. Grab off the top here. So let's take, I don't know, I'm gonna pick this one now. We're gonna pick these 3 bytes from hash. That gets us, my math is right, and even simple math is hard when you're standing in front of a group. That gets me right, that's 15, right? My math on that. That's 15 bytes. That means when we do our hash, we're gonna always zero it out, initialize it to those same 15 bytes every time. We just, this will all come together again when you're rest of looking at the standard lib implementations. These choices are not just like choices that you make when you're designing a hash algorithm. Sometimes they're choices you make when you use a hash algorithm. Sometimes these are not like hard coded in the algorithm, but they're inputs into the algorithm. So we'll go into this in a bit. That's done. If I refresh this, we should see all our numbers in here. State size 15, mix 73, FF 722, 88, riveting. But we're going to come back to all these and use them later. So here's also our initial state. We already just saw that. It's just the same code. We just live loaded that. We're going to make our own hash implementation, right? So our hash implementation is going to be something that implements hash.hash. That's all it takes to be a hash implementation. So I'm doing this little one-liner. If you don't do this little one-liner, I highly recommend it. Java people, Python people will look at this and think this is required to like declare to the compiler that you implement an interface. That's not true. But it is here in the compiler. It's a 0 allocation snippet where if your thing, in this case, the ugo struct, doesn't implement the interface on the left, the compiler will warn you here. Nobody doesn't have to be trying to use it as a hash.hash. Like you don't have to have code that's trying to use it as that. This little assertion will, that the compiler elides when it compiles, will kind of give you a warning that like, yeah, you know you are implementing this or you have mixed up interfaces or you're in a function, whatever. So I like this a lot. I put this in most of my code when I'm specifically, it makes it obvious when you look at this, like the intent of this is to be an implementation of that. It's in here in the code. Not required in Go, but definitely helpful. The next thing we do is there's really only 2 things any instance of our ugo hasher needs to have, and that needs to be that internal state, which is going to be 15 wide. And it's going to always, right now it's going to be 0 when you make that struct empty, and you'll see us setting that in a second. And then we need to have I. Remember all our operations where you had mixing and stir and XORs all together? Every implementation is always going to start at 0, go through those lists of operations on every chunk, and then come back around. So again, it's always going to do those operations in the same order on the same bytes coming in, but they need to track which operation is the next one. So they're just mixing up behaviors. So that's our struct. We always need to implement the 5 methods, and I've kind of shortened this one here from IO writer, that make us a hasher. And I've reordered them because some of these are way easier to implement than others, right? So remember, state size is 15. We're not a super great hashing algorithm. So 2 of these methods in the implementation are done. It's like, what size of data will we return? 15. We're going to give you 15 bytes all the time. That's the amount that we're going to give you. And then what is the ideal size to give us? Also 15, because we're built for 15 at a time. We're not any more efficiently, like technically the spec says it might operate more efficiently. Our hash algorithm isn't actually any really better or worse on those. Technically slightly a bit better. But again, we have to implement that to be a hash.hash implementation. So both those are just 15. That's almost a majority of those done. Next is reset. So we need to have a reset method that takes our hasher and say, okay, forget everything you've been fed, like go back to a 0 state without me making a new one. So our reset function is really, really easy. We're going to set our operations back at 0 where everybody starts. And then we're going to also copy into our internal state all of the initial state, right? So we're just saying, yep, we picked these 15 bytes to always be our initial state. So reset gets us to 0, to a good, not, you know, we have a 0 isn't a valid value for this hasher. So this is what reset does. So that's a majority of the implementation done. Then we get into write, and write is where all of like everything happens in this write function. If you go look at the full implementation of the hasher, it's in this write implementation. So there's a lot here, and I'll do my best to break it down. First, we're going to get the size, which is the length of our input minus 1. Oh, sorry, let me make sure I get this right in my head. We're getting where we're at. We're getting how much we have to bring in. And we're saying, hey, if we've gone past, if we've already eaten up all the input, we're not. What we want to do is we want to take this. They're going to give us bytes of any number of length, right? They might give us 1 byte. They might give us 1,000 bytes every time they do a write. So we need to operate on chunks because that's where our math is. We need to operate on 15 bytes at a time. So we're going to, in this infinite loop, we're going to just keep writing. We're going to take 15 bytes off there, write them, and then take the next 15 bytes off there, write them. If you give us less, we're going to do a bad implementation, and I'll point that out when we do it, and just read those bytes. That's not the right way, but you'll see that in a second. We're going to do this implementation, we're just read it in chunks. So that's what this whole logic is it's essentially take variable length input and process it in 15 byte chunks. That's all that's happening here. Inside here, we write that chunk to our internal state. Then we move forward. And then again, if we just did operation 0 on that list of ops, we'll do the next one, the next one. So as long as you do the same amounts of chunks, the first chunk's always going to be a mix. And then the next chunk's always going to be an XOR. And the next chunk's always going to be a mix because of those ops we chose earlier. So that's what a write is. And at the end, we follow the implementation. We don't return an error ever. And we return, yeah, we wrote all those bytes for you. So that's kind of the bulk of write. This is kind of where the magic goes in. This is where write has broken us up into 15 byte chunks. And now we're going to need to actually take those 15 bytes. Remember that slide from before where we take those 2 bytes and split them and merge them in? This is us doing that in code. So we're going to take that chunk. We're going to pull it out of the full input. So we're pulling the chunk out. We're doing this really dumb thing that you're not supposed to do for writes, which is when we get a partial chunk, we just write it. You're supposed to kind of like track that in case they write something later. There's a whole thing. For simplicity's sake, we're just going to process partial chunks and have a bad hash implementation because I don't want to overcomplicate it. There's a lot more you could do here, but we're going to take it in those chunks. And then on those chunks, depending on which operation we are in that list of things we're going to do in order, we're going to start at 0. And the first thing, whatever we picked, I forget. Let's go back. So we're going to do an XOR first, right? So we're going to be on position I. We're going to do operation XOR, which means do an XOR. And then if we go back here, the next thing's a multi, and then we'll come into here. So you can see every chunk's going to iterate through and do one of these 2 operations. It's always going to do in the same order, though, as long as we have that same settings in our hasher. So we'll do those operations, and then we'll do some mixing at the end. So we're going to take the bytes that you gave us and mix them in, but then we're also just going to stir itself together. And we're going to do a lot of very specific mathematical stirring, very precise stirring, but it is just stirring bytes around. So you'll always get the same results. And this is all just in the name of trying to get that cascading effect, right? We want one tiny change of input to have a radical change on the output. This doesn't accomplish it, spoiler alert, like you guys look great. There's whole papers on this, and I guarantee the implementations of the good hashing algorithms are not like a few hundred lines long or whatever this is, but it's good enough to get the idea. We're trying to throw these ideas in. So once we get into one of these 2 XORs or multis, we're going to do either an XOR, and the XOR has bytes we're working on, and our internal state, and the chunk that we're going to work with, and we're just going to take all of the bytes and XOR them with the things next to them, right? So that's what's going on here. We're getting this operation is XORing these lines, each byte in state. There's 15 of these in our implementation with the 1 above it. Then we're also, again, to add in some more distribution, some diffusion of data, we're then going to do that rotation the 77 times or whatever. We're going to kind of do that Pac-Man thing, 77 characters, everybody kind of like musical chairs that 77 times. But you'll always end up in the same chair if you start in the same place because you're always doing the same operations. Next is multiplication. Multiplication, and I just like made up these ideas. I didn't even look at real hash implementations. They probably do. They use XORs a lot. I don't think they do this weird multiply thing. So I made this up. Multiply is the same thing though. We take the bytes. We have 16 bits of data, and we have another 15 bits and another 15 bits. Those can both be converted into integers, arbitrary sized integers, and then multiplied together, which is some number of bytes. We'll even we'll just let you buffer overflow, right? So if we go over the max bytes, it'll go around and loop back around to 0 again, which we don't care. We just want to have the same results every time. So we don't need to care about buffer overflow here. We just take this byte. If I go back here, right, we get the number for this byte and the number representing this byte, and then multiply them together, and then take the first byte of data back. So again, just doing a bunch of computations, but it's the same every time. And then when we're done, we're taking that mix, that FF, and we're adding in our own byte on top of there, and then doing that same kind of Pac-Man shuffle musical chairs rotation. So XOR multiplications. And if you remember, we switch back and forth between XOR and multi depending on what our config was in our hasher. And at the end, we just mix internal state. We don't even care what the output is. We just say after every block, we do some internal mixing. And the mixing is where we, again, take a byte and we find the byte, what was it, like 77 positions to the side, again, wrapping around. And then we mix those two together and shuffle the bits. So it's just, you can see there's so much stirring, mixing, math, computation, but it's always the same every single time. And it seems like a lot, but computers are really good at doing math and a lot of these operations are optimized. So it goes a lot faster than you think. So that was right? So writing chunks, we do the writer, we break it into chunks, we do XOR sometimes, we do multiplication sometimes, we always stir the state internally the same mathematical way. And it's all deterministic with the same input bytes, it's always the same output. So when it comes to sum, this is like the implementation of sum. It's just, well, you give me a byte slice and I'm gonna call append with the thing you gave me and put mine at the end. And that allows you to reuse the slice, zero it out in order to not have to reallocate memory. So that's like, this is a pretty good example of most implementations of like what they do under the hood is just, yeah, I'm just gonna throw those bytes at the end for performance. And that's all 5, right? We had our sizes, we had a reset, we write, a sum, and that's a hash.hash implementation. So let's test it out and see, you made these choices, like I put together the code, but we all kind of mad-libbed our way together to see how we got. So here's some really basic examples. Here's where we're just gonna do 0 and 1 and see what they hash to with Hugo. And then again, test with capital, and then a period or an exclamation mark. So we should get, if we have a really good hash algorithm, we'll get a couple things in the first round, right? First is we're gonna get, because we chose 15, we're gonna get 30 characters, right? Every byte is 2 hex. So when we convert this into hex, we're gonna get 30 because we chose 15 as our byte slice. The next thing is, if we're good, the hash between 0 and 1 and test and capital T test should be radically different the whole way through. And do I hit run? Let's see where we ended up. So I put SHA-256 on the right so you can compare a good hash algorithm with what we did. And it's not great, right? So like here's 0 and here's 1, and they have a lot of characters. Not always, like you can kind of see there are characters in common, especially here in the middle. But the beginning and end, and spoiler alert, no matter what the arguments we put in as our Mad Libs, the middle's always squishy because I'm not doing a lot of the things you have to do to really stir and have cascading changes. But we have pretty good, right? Like some of this is radically different. Remember, these were just a difference between capital T and a lowercase t. So these hashes are actually, again, the middle squishy, but the starts are pretty good diffusion. Not so great with this one, again, because you can see the end changes because we're not, again, not always great at really, really diffusing. Where SHA, these all look completely random on the other side because SHA is a good hashing. But I just wanted to illustrate, like, this is what they're all doing under the hood. This is people studying, thinking about the operations, and all of them to some degree are just doing this kind of stuff with stuff people have thought about a lot more of, like, what are the right kind of operations to really cause these cascading changes? What are the right numbers of operations that are performance friendly? What are the right 0 values, which we'll see in standard implementations? But you can do it, right? Like, and if you spend a lot of time, you might be able to come up with a better one that is optimized for whatever your use case is. You probably don't need to write it like any authentication, encryption, all that stuff. You shouldn't write your own because you probably don't need it, but it's neat that it's doable, right? And that we can kind of come up with something that kind of works. So that was us writing our hash implementation. Now we can talk about, that's hash.hash. Remember, there are 5 other things. So inside the hash package and Go, there are also 2 interfaces that not every implementation implements hash.hash, all of them. But only some of them are hash 32s or hash 64s. And that literally just means, like, can your implementation return, is it wide enough to return me a 32-bit or 64-bit integer, right? And so you can imagine this down here is wide enough to do that. Our hashing algorithm technically can return both of those. Not all of them can. Most of them are actually named. You'll see that most of them are named after their width that they'll return. So they're usually one of these 2 implementations only. But you can imagine, again, the size of state we chose Hugo 64 or 32, Hugo 8, right? It had been 8 wide, 8 bytes, and it could have been 64 bits. And right now it's too big to actually even fit into 64 because we chose 15. So 15 bytes is way more than 64 bits. So our Hugo implementation couldn't be either of these, but we went smaller on our byte count. We could have absolutely implemented either of these in Hugo and just taken our bytes and said, yeah, we'll turn that into an integer for you. So that's the 2 in there. Another one is cloner. This is mostly just, again, everything implements this. It's just, remember our internal state? Maybe you've fed a bunch of bytes into your hash and now you want to save that state so you can resume it at a different point, or like try, okay, well, I fed you these bytes now, but I want to split you off into 2 different implementations. This is just a way to have the hash copy all its internal state just to a completely separate instance. There's not a lot of practical use cases that I've ever run into needing to clone these, but you can do it. I also didn't cover all the hash implementations can be written out to bytes, so they can actually be saved to disk or whatever and loaded back. They all implement binary, marshaller, unmarshaller. I won't go into that. Again, kind of technically another little helper that some hashes implement. And the final one is this really fun one that Mariah wants to know about, which is the XOF, extendable output function, which is a totally different kind of hashing thing entirely than what we've talked about this entire time. I'll show you that at the end. Any of the hashes implemented this are writers and readers, and then they have reset and block size. There's no sum. Notice there's no sum in here, which was the part that gave us the bytes at the end. There's read. And I'll show you what that can do in a second. But let's talk about stdlib. I've been talking about it a lot. There's a bunch, and I'm not going to cover the ones in experimental. They're in the experimental and some other places in the Go stdlib adjacent are other implementations, but these are the ones that just ship with Go. Adler 32, which you can guess how wide that is and what kind of hashes it implements, what interface it implements. CRC 32, CRC 64, those are both kind of network level ones. Those are born out of lower level, like just kind of everybody agreeing that we got the same data and it wasn't mutated in flight. FNV, which I really, really like, is particularly good on collisions. SHA-1, which basically, SHA-1 is basically broken, yes. SHA-1 is basically broken. MD4 is absolutely broken as far as cryptographically secure. SHA-256, 512, and SHA-3, which is the thing I had to learn about because I'd never dealt with that before. We'll get to that in a second. And last but not least, MD5, which is kind of an old school hashing up. So these are all different implementations. The one that you need, that you would choose for your use case really depends on what you're trying to do. If you're trying to do that kind of pseudo ID thing, you'll need to choose an implementation that can give you a number back, right? Because you probably don't have space for a full SHA-1 sum hex code, but you would have space for a number. You can also go research on any of these and I won't go into the details of like which ones are better for which, for collisions or speed or whatever. They're just all kind of official standards. As you read down this, you see all of them are RFCs or FIPS, like definitions. So it's just Go implementing something that's already defined. It's not anything made up in Go. So let's do some comparisons. Let's import all that stuff. Try them. And ourselves. And I put Hugo in there because we got to put ourselves up to the others. So here's where all of our hashes are going to fit into this hash implementation struct, which is just a label. And remember, every single one of them implements hash.hash. So I can write code that takes any implementation where the code doesn't care what the hasher that you choose is, just that you give it a hasher. Then we're going to make this big list of implementations. So we're going to make Hugo new. And we can call it .new on Hugo, and that creates our struct and calls .reset on it. I don't think I actually showed that in the code, but it creates our struct, and our 0 values of our struct are not useful because we don't want to initialize that inner state to all zeros. We need to initialize it to our initial value. So you'll see that all of these, none of these, the empty struct in Go is not valid. You could make it, but it won't work. So all of the stdlib hash implementations have kind of a similar pattern of a .new. So we're going to do Adler 32. Now we get into some fun stuff with CRC 32 and 64. Remember when we chose an initial value? Well, Adler 32 has a fixed initial value. That's just what it's always going to be defined by the structure. And a lot of these do. But CRC 32 and 64 don't have an actual always use this initial value. It's not always go and Tato or whatever our combo was. They have different, and these kind of, you look at these are just numbers. These are just some series of bytes that can be represented as a specific number. And they have different properties of whether they're better for collisions or which body like defined those. So the IEEE standard is gonna be, again, the one IEEE defines that. Been in custom, I don't remember. I remember digging into these. I already don't remember like what the specifics are, just that there are different initial values that you can feed into CRC 32. And as long as everybody agrees on what initial value they use and they make it with the same table, they'll get the same answers at the end. But the table you choose changes kind of properties of the algorithm. The one I do remember for sure is 64. This ISO is like all zeros or something. It's maybe all zeros or it's one. It's a really simple number. And it's not great at distributing it, kind of doing that diffusion, but it was really, really good and specifically made for old hardware where they wanted the computations to be easy. So the ISO standard for CRC 64 is easier to compute with old hardware. And modern hardware, it's the same. So there's this ECMA newer number. It's a lot better at making more diffused hashes. These are the only ones where you have to feed those in, and you can tell it goes so specific on one that they made a function just to like get the IEEE one, because like that's probably the one you should use because there's an easy way to access that. And I think both of these have a .new and .new here both have like a default implementation they'll choose if you put nil in here. So again, this is where those zero values like start to click because we implemented, we had to set a zero value. Some hashers have ones you can choose. Next we have FNV. It has a 32 and it has A versions of all of them. And I honestly don't remember the difference between those. I just picked one at one point and kept using it. But they have some different properties between the A alternatives and the non-A alternatives. Then we go into SHA-1, SHA-256, 512, and all the SHA-3. And SHA-3, if you look at this, has some weird numbers in here, like 224 and 384. I won't get into that, but it's SHA-3, spoiler, is really, really different. It's also different in that the zero value for SHA-3 is valid. It's the only one where you don't have a .new that you have to use. Technically, it does work. It does this 224 by default. And then last but not least, again, MD5. So what we're going to do for each of these implementations, we're going to have a label and the instance of that implementation. For each of them, we are going to iterate through them, bring out their label. We're going to write some data to them. We're going to sum it, encode it. Right? So we're just going to hash the same value with all of them in a row to see what happens. Then we're going to go through them all again, do this interface assertion to say, okay, well, which one of these implements hash 32? Like, we're just going to throw all of them at them and let the compiler tell us which one of these, or the runtime, which one of these can give us a 32-bit integer. So if it can, we're going to print it out and take the hash that we got from before and format it as an integer and return the integer, right? So and say, okay, we can give me a 32-bit int. Let's get a 32. Same thing with 64, exact same code, but we're going to do a 64-bit integer if they're a hash 64, just to see what does what. Then we're going to do the same thing with cloner. Again, I think all of them are cloners. We'll just print out. We're not doing anything with the clone, but technically, if you clone and you do a different sum, you'll get it. Like your clone can write bytes and your original can write bytes, and they'll start it from the same place, right? But they're independent of each other. And then finally, we do this XOF implementers. So we're going to say, which one of you implements XOF? So let's run this page here. And I'll scroll to the top and we'll start looking. So all of them are hash.hash, right? So we knew that because the compiler didn't complain when we tried to assign them all to a hash.hash in our struct. And here's, you go in here with its 30 characters out of the 32. And you can see some of these are, a lot of these are shorter, a lot of them are longer, and you can kind of start to really see patterns as you look at sizes. So there's 32, there's 64, 28. You can see that they're starting to grow. Again, same thing with SHA, SHA 512. You can tell what type of times they just have chosen different standardized internal state widths. So you'll get a different amount of bytes back every time. Here's SHA-3. Again, all those implementations with SHA-3 also implement hash.hash. And here's a good old MD5 at the end and doing the same thing. So that's kind of cool. Here's all of the implementers that are 32-bit. And kind of not surprisingly, they're all the things that have 32 in the name of the package. They can all give you 32-bit integers. Remember, the width of that, it's not a standardized width. Like, keep in mind that when you go to an integer, integers are anything from 0 to the max in 32, right? So you're not going to get a standard width unless you pad, whereas all the other hashers up here always give you a standard width. Numbers have a max that they can be, and that's the maximum in 32 width, like a literal number of digits, but it's going to be variable. All these did come out to be the same for whatever lucky reason. Here, you can start to see the variable with here with 64, where even though these are all 64-bit integers, they have different lengths of numbers. So you have to kind of account for that, although it is a knowable max width. So if you're trying to say like, okay, the maximum possible pseudo value I'll make is whatever I put on here plus the largest width of a 32 or 64 width. So again, not surprised that things that have 64 in the name all are 64. Here's our cloners. Our cloners, again, these are duplicates that are spun off, write some more state, but kind of independent of the original copy. And then there aren't any .xof, like nothing. I remember I made the whole list. We went through the like giant list of this, and none of them are hash.xof implementers. SHA-3 was a regular hash. And that's because this is a whole other idea. So we'll come back to that. And we're gonna come back to it now. I shuffled the slides around. We're gonna go back to that, and this will be the last thing we do. SHA-3 implements this new idea of this whole shake, and you have to create it a new way, right? This is not SHA-3.new. You look back at our old slides, it's SHA-3, but whatever .new, SHA-3 size, new, whatever size. In this case, if you want something from SHA-3, which is the only thing in the standard lib that will implement this, you have to make it with a different constructor, make a different kind of struct. So we will make a new shake 128. It's fine to just make that. There's also a new C shake 128, and that's on both the 128 to 56-bit widths, where it takes 2 slices of bytes. This is pretty normal as well. This nil is canonical nil, just pass nil. You don't need to use this. I'm not even going to go into it. It's very specific, ignore it. This is sort of a namespacing idea, which is something none of the other hashes have. So you talk about collisions, right? And you can reduce the possibility of collisions. If you know that I'm going to hash these and I'm going to put one of those into bucket A and the other into bucket B, I can take the hash, and as long as I always do the same, write the same bytes in with that same kind of namespacing, I'll get the same result, but I can guarantee that the same bytes into 2 different implementations with 2 different namespaces will have different hashes. If you've ever used some of the other UUID versions, there are some UUID v somethings that have namespacing as part of UUID generation. So again, this is an optional way. You don't have to do it. You can do this one that's not customized at all and just it'll use the 0 values, but you can namespace 2 different things. So here's some implementations of those. And then we're going to go through those implementations. You'll see something here where I'm declaring what my output size is. So we're going to say 32. So for each of those implementations, there's 4 of them. We're going to we're going to go each of them, then inside each one, we're looping over twice, and we're going to reset it. We're going to write some bytes in. We're going to make an output slice. Because remember, we don't have a function that gives us a slice back. We have a read function that takes a byte slice and will put data into the thing we give it. So we'll make a byte slice. We're going to say, okay, this is going to be, the first time around, it's going to be 32. The next time around, it's going to be 64 bits wide because I'm multiplying it by the integer +1. Then we're going to read into that. So it's going to populate it with data and then encode that to hex and print it out. So I'm going to run this. And there's some fun, interesting things to point out with this. So these shake implementations, including all the XOF implementations, which is the SHA-3 alternate ones, have a variable length output. You can do anything from, I can go in there and ask for 1 byte or 10,000 bytes. And you can now control the SHA-3 how wide that is. There's no more fixed lengths, anything. And wider means more, bytes to represent it, but also every single byte you add increases your odds of collision like exponentially, right? Because you go from some possible number to it. You just add another byte on there, you have a whole lot more possible numbers, and we'll get into the math. So you can now say, I'm really sensitive to collision. I'm in a bigger system. Sure, I can have a 1K fingerprint. Like I can SHA this to 1K of data. Like the odds of any 2 things SHAing to 1K are astronomical. So, and I can store that. And that's still relatively small in modern systems. So you can choose to like make your own size. You can also get that multiple times. I didn't show it here. If I go back to, if I close this, I could do this read again. So I could loop through and I could read 64 bytes, print them, and then read another 64 bytes, print those, read another 64 bytes, print, and I can do it in chunks and actually generate. And then every read, like it's always going to generate the same bytes at the same positions in the same order, but it allows you to kind of hash data and get multiple chunks. There's kind of some cryptographic use cases. There's some not password use cases, but there are use cases where I want to everybody read in the same data and then through two discrete chunks of output. So that's what I have here. If I hit run on here, you can actually see that if I printed the first 32 bytes, and when I printed the first 64, the first 32 are still the same first 32. I just got more the next time, right? So if I printed this one byte at a time, I would get those bytes always in the same order all the time. I can just get them in chunks and I can get them as long or as short as I want them, which has some nice implications. SHA-3 is sort of just sitting there on the back burner. People being well invented it, I guess, in case somebody comes along and breaks SHA, like the other SHA implementations, that we suddenly need a nice, widely known, accessible, like more harder to break or like potentially longer, larger in space hash. But most things are not using SHA-3. It goes kind of on the edge with that. Everything else is using all the other SHA implementations. Kind of cool that you can go in there and get these like variable lengths outputs. And that was it. So we took Mr. Potato Gopher. We learned a lot about hashing. He answered all his questions, shuffled them up, and there you go. So this is the link to the source code if you want to go see any implementations, if you want the slides, if you want the files to print your Gopher. I will be totally honest, it's not, you can actually print it. I could talk all day about some of the mistakes I made, like learning how to do that correctly, and you can see that in this early one that I thought would be nice to have just little tiny pegs. I was not thinking like that's not how 3D printing plastic wants to work.
Oh, physics.
Yeah, physics. So I'm learning a lot. Some of these points are particularly hard on different printers. So I kind of got in the habit later of, see if I have an example, turning them in the modeler software and just sinking them a little bit below the print bed surface, because you don't need the full point. It's nice to have the full point inside the hole. So spoiler alert, if you go print your own, it's a little fiddly, but I would love it if anybody that's better at Blender and or 3D model generation could take it and remix it to something that's easier to print. Once you get the files, there's also, if you want to just like print it in your Prusa user, you can just go get the Prusa like entire project file, load and print it where everything is just ready to go. And it's pretty good on multicolor. I don't have a multicolor printer, but I just did Sharpie black on like the eyes and the nose, and that was good enough. So just print the different pieces, different colors, so it comes out pretty good. So let's give these away and I'll call it done. Does anybody want one? First of all, who wants one that can?
Your abstract syntax tree.
You do have my abstract syntax tree thing. Does anybody want this sad weirdo first? If not, that's totally okay. He's been sitting on my desk. Let me get these away. We hash bucketing. Okay, hold on.
Hash bucket.
Okay, so we go all the way back to. It would come with something. If I just put myself on the spot, I'll figure it out.
Judge whether your bucket is worthy.
Yeah. Okay. So throw out names and I'll put them in here because I don't know everybody's names. So just yell your names. David, I'm sorry. I should know names, but I'm really horrible with them.
Okay. It's not like I've been here.
I know you spoke
You should
in.
have written this one in a loop because you got it twice on each line. And
Oh yeah, thank you.
You're also, yeah.
We're just gonna pick whoever comes the lowest number out of these. That's how we're gonna do it. So we got David. Throw out another name.
AJ.
AJ. Okay.
Hope you.
All right. Who else?
I think there's 2 or 3 of us can win.
Nobody trusts AJ.
Yeah, there's 4 there. So who wants a weirdo? There's 3 good ones and a weirdo. Thomas. Different than Tom?
Yeah.
Okay.
Oh, what the? How are you doing?
I'm all right. How are you?
Good, I didn't see that.
I got here late.
All right. Anybody else? We got a couple more. I can put more lines on here. Okay. If that's good. We'll do a call there. That's enough that only one person has to lose.
Brandon wanted one.
I was just throwing my name out so people would say their name. I run
Okay.
this thing, so other people should win.
All right.
This just tells you how many people have 3D
All
printers.
right. Lowest numbers. Whoa. Change them.
It's D, that's David, right?
D is the bottom one. So Thomas is the winner. First winner gets pick and I have some parts here, so you can assemble yourself a part.
On the basket.
I should have changed the prints. Can you tell I didn't plan this part? Okay, next lowest number 73. David.
Oh, sweet.
There you go. So you do get one. Yeah. And then 26 is AJ. AJ gets a good one. And then Tom gets, if you want that wacky ass one. If not, I apologize.
AJ, do I give you the one that's pretty?
He's the most endearing to my heart.
Whichever one. I'll close my eyes. You have one too.
If you don't want it, that's fine. There's.
Well, hold on, let me fix it first. Yeah. Remember, this is for my children. Well,
I thought it was for you.
Children.
Good at night.
In the schematic way, that's I love items. And that's what it's.
Those are small parts.
You did good.
He's just very silly and I like it.
Just expect.
He's been.
Oh, wait, wait. Oh,
That might be because he has two arms. He has 4 arms.
So I can turn off the
Wait.
screen.
There you go.
Guys.